Hi, my name is Lanzén, and I'm in Asti in the Basque Country in Spain. I'm going to talk a bit about work I've done with my colleagues in Norway on using sediment eDNA metabarcoding as a tool to monitor the impacts from the offshore oil extraction activities. And this is part of the Metamon project coordinated by Norse in Bergen, which has been going on since 2018. And it ends this year, but fortunately we have a new project that will kind of pick off where this one ends. And the underlying question of Metamon is if we can use sediment eDNA as a tool to do monitoring, that is to say, predicting the environmental status and the impact from oil extraction activities. And we use two different markers for this, the 18S, which picks up the total eukaryotic community, including protists. And they may be better for metabarcoding technically because they are smaller and have a more homogeneous distribution in the sediments. We also used metazoa targeted by COI, and this allows us to use existing indicator knowledge about indicators and biotic indexes. But for both of these markers, for both datasets, we also try to identify new indicators and develop new biotic indexes. And the Metamon project also has other components like identifying and filling in barcoding gaps, so common organisms that lack reference sequences. And we also looked at optimizing sampling and lab protocols. And based on that work, we are using 3 different grab replicates, and from each we take 3 different extracts that are pulled from different places in the same grab. And the samples we looked at were collected during regular monitoring campaigns from 2018 to 19, and they're from 99 different stations, from 10 different installations, and 3 regional reference stations. And these were located in turn in 3 different regions, which is region 2 and 3 in the North Sea, and then region 9 in the Barents Sea. And these stations are following a gradient from very good to very poor status, or they include that. However, they are a little bit biased towards good status, with many that are also poor, and it's difficult to find good examples of the intermediate impact. But still, we have done our best to choose stations to follow a good gradient in this way. So in order to quantify impact from oil extraction and drilling, we developed a physicochemical pressure index, PI, that is based on total hydrocarbons, polyaromatic hydrocarbons, PAH, and barium and copper. And this we did because we don't want to use the NSI, Norwegian Sensitivity Index values that are calculated using the macroinvertebrates by morphological examination as a ground truth. But as you can see, this morphological based assessment agrees very well with the pressure index, both in terms of ecological status, which is represented by these different colored boxes in the graph, and this is the graph to the left, which is comparing to morphological taxa. And in the graph to the right, you can see what happens when we use the COI metabarcoding relative abundances to calculate NSI values instead, and that also works quite well with strong agreement and pretty good correlation. So this already is a way that we can use the COI metabarcoding. And as I said, in the routine monitoring, they're not only looking at biotic indexes like the NSI, but they're also looking at the alpha diversity of the morphologically identified taxa to assess the status of sediment samples. And in the graph to the left, you can see how the Shannon diversity, which is the most commonly used, is correlating to pressure index, which is weaker than the NSI, but there's still a very significant correlation. And this they surprisingly not work for the COI. There is no significant correlation there, but to the right you can see the 18S metabarcoding, which is highly significant in correlation to the pressure index. If you look at the community composition that we get with 18S and COI metabarcoding respectively, and compare it with morphology at these higher taxonomic ranks, we can also see that they are quite different. And the 18S here is limited to only the metazoan taxa. So the COI and morphology were dominated by the same group, the polychaetes, but in the 18S it's the nematodes that are dominating instead. But in spite of this, if we're looking at the whole community, not just the metazoans, and if we use a taxonomy independent approach, so here the OTU compositions without taxonomic labels, and we compare them with an approach that looks only at the dissimilarities, the Mantel test, then it's actually the 18S that agree better with morphospecies dissimilarities between samples, and the COI is not as good. And this, we think, has something to do with the heterogeneity that causes COI to pick up relative abundances in a kind of more noisy way than the 18S. So to use also the 18S metabarcoding data, we try to develop new biotic indexes using a de novo approach to figure out which taxa that can work as good bioindicators. And this we did also for the COI. And the process for creating these novel biotic indexes is something we have used before on coastal and estuarine sediments with multi-impact prediction. And it's basically taking the taxonomic composition of the metabarcoding data set. So 18S and COI is done separately, is analyzed separately, and it starts by looking through the taxa, taxon by taxon, and looking at its correlation with the pressure index. And this is done with a tool called Titan, which will identify a threshold where the abundance of this taxa changes as an effect of the pressure index in this case. And then we get a subset of our taxa that are considered good and reliable indicators, and to figure out if they are an indication of good or bad status or something intermediate, we use something called quantile regression splines, which is modeling the distribution based on the 90% quantiles, and then looking at, and then it fits a spline, a polynomial spline on this, and where this predicted distribution will peak, where it reaches its maximum, this is where we look at what ecological group that corresponds to. So in the example here with the radiophyca, we can see that the peak is at sort of pressure index 0.8, which is in ecological status group 1, or very good status. So then this is added to our biotic index as an indicator for pressure index group 1. And when we did this, we didn't use the whole data set altogether, but we divided it in installations or regional reference stations. And then we used one installation or reference site out to build a biotic index based on the other ones, and then using the left one out, the left out one as a validation data set. And what you can see on these graphs is the performance in the left out ones, because we rotate them also. So this is a cross-validation approach. And in the y-axis then is the predicted value, and in the x-axis is the true value. And as you can see to the left, you have the status for the COI novel indexes. And these performed a little bit better than the 18S based ones on the right. The correlation is highly significant for both, but it's weaker for 18S. And however, the agreement based on ecological groups is better for the COI than it was when we simply calculate the NSI. So this approach actually works better and can take into account bioindicators that are not present in the NSI that may be relevant to our sites. An interesting thing is also that the COI identified many already known bioindicators like Capitella. And we can also look at which taxa that are picked up as potential indicators, which is especially interesting for the 18S, which is shown here. And to the left here you can see the ecogroups 1 and 2 that indicate sensitivity to impact. And here we can find interesting things like the Labyrinthum mycetes and Imbricata that are not part of the traditional bioindicators. And in the ecological groups 4 and 5, we find things like Namako, which is an uncultured lineage found in anoxic lakes. And in general, in fact, a lot of these taxa that appear to be insensitive to low oxygen, poor oxygenation, are picked up in these ecogroups, which is interesting. And with that, I'd like to say thank you to my collaborators in Bergen who are coordinating this project, our funders, the Norwegian Research Council and Iker Basque, and our industry partners Equinor and Total.